So my lesson is for a special education Common Core Algebra B class. We are currently in the Quadratics unit, and this lesson is specifically on interpreting quadratic equations in real-life scenarios, such as footballs traveling through air or rockets being launched. I think these students will benefit from this lesson because they'll be able to visualize the motion of objects in a relatable sense that's clear to them. The learning goals of this lesson are to be able to graph quadratic functions, identify key features, and to model the functions involving situations dealing with motion. While the students are graphing the given functions, I will be circulating the room to see if they are making progress or if they need any help. From this, I'll be able to see which students are doing well and which students need more instruction. During the lesson, I will guide them through a step-by-step process with the calculators to locate key features of graphs, and at the end, I will give them time to have an open discussion while they complete their exit ticket assignment to see which students fully understand the lesson and which students are still struggling. So at the beginning of class, all of the students are expected to get their assigned calculators, white books, and pink books. The white books are their classwork and the pink books are their homework. Then they are presented with the introduction to the lesson on the smartboard that states what page to turn to in their white book and what homework is assigned for that night. So I'll begin the lesson by reading the class my focus question, which is, how can we interpret and understand quadratic equations in real-life scenarios? Meaning, how can we understand the motion of a ball being thrown or a rocket being launched from the top of a cliff? After my introduction, I will move on to the next slide and show students this graph of a labeled parabola, which has key features from previous lessons that they have already learned to identify. I will tell the students that we are still going to be finding the same features. However, we will begin applying real-life meaning to them. After this, I will begin with the first example that regards a football being kicked from a starting point, traveling through the air, and landing on the ground. I will circle the starting height, which is 3, and I will also circle the initial velocity, which is 40. Then I will ask the students to substitute these values into the given quadratic equation, which is labeled as h. Once these values are substituted in, the students are then able to type it into their calculator, complete the table, and then graph the 3 points on the grid. These two tasks require the students to access their prior knowledge of basic graphing skills. Once this is completed, I will help the students visualize the path of the football using the graph they drew by explaining that the x-axis is time and the y-axis is height. Then I will ask the students, what is the maximum height that the football reached? And they will identify this from looking for the turning point in the table or the graph. This answer will then guide them directly to my next question, which asks them how long it took the football to reach its maximum height. The students will then refer to the corresponding x value of the maximum height. My next question will ask the students how long the football is in the air, or at what time does it hit the ground. At this point, I expect students not to know how to find this value, and so I'll ask them if they can identify a 0 from their table or graph. When the students realize that they can't, I will ask them, so then how do you find the 0 in the calculator if it doesn't have a clearly defined location? I then expect them to reply with the calculator steps known as second trace 0. Then I will open my smartboard graphing calculator, enter the equation, and walk the students through a step-by-step process of finding the value for when the ball hit the ground, which is in this graph from my calculator at the board. This would be this point right here, which is labeled 0 with x equals 2.5. I will then move on to the second problem, which deals with a rocket being launched off a cliff. I will read the problem and inform the students that the graph will be exactly the same in respect to time and height. The first part of the question is directly from previous lessons, so the students will be able to plug the equation in, look at the graph, and factor the zeros. Then we'll move on to the next part, and I'll ask the students to look at the graph in their calculator and ask them to tell me where the maximum is. After the students identify the top of the parabola, I will then show them how to use the calculator's second trace feature to find the maximum value. When we find the coordinate of the turning point, I will ask the students if the x or y value is the maximum height of the rocket. Once the students understand that the y value is the maximum height, I will then ask them how long it took the rocket to reach this height. I expect the students to then make the same connection as they did in the first example and conclude that the x value of the turning point is the time it took to reach that height, which is right here in this graph. This is where the rocket starts. It goes through the air, goes down, and hits the ground right here. So this cursor is marking the maximum. This is the turning point. The y value right here is the maximum height, and this is how long it took to get there. For the next part of the question, I will ask the students over what domain is the rocket rising and falling. But before really giving them a chance to answer, I'll return back to my graph on the calculator at the board, and I will ask the students if it makes sense to consider negative numbers when dealing with real time and space, meaning can we have negative values of time? When the students respond no, I will then point to where the rocket is launched from, follow its motion through the air, and stop where it hits the ground. Then I will ask the students at what x value does the rocket start to increase and then start to decrease. The students are expected to understand that the rocket increases from 0 to the x value of the same turning point that they found in the previous part of the problem. Then I will ask them to identify the interval for which the rocket is decreasing. The students will then see that it decreases after the same turning point until it hits the ground. This brings us to the next question, which asks, how long did it take the rocket to hit the ground? The students will easily identify the x value of where the rocket hit the ground, which is visualized on the x-axis. Then, at this point, I will inform the students that the remaining parts of the problem are their exit ticket. This portion of the problem is designed to encourage the students to think logically. From this, I'll be able to assess which students are truly grasping the topic and those who are not able to think of the object's trajectory in a literal sense. And that will complete my lesson for the day.